Welcome to Brain Vision.
In this problem, we're going to be looking at a traveling electromagnetic wave, and it's described mathematically by this formula here. This formula hopefully looks a little bit familiar. It's similar to what you would have seen when studying standing waves, like on a vibrating string. And in fact, by comparing this to those standing waves, we'll actually be able to figure out things like the frequency and the wavelength of it based on these values in the formula here. So the first thing I'm going to do is I'm going to go back and write out our equation for the standing wave on a vibrating string. You have an amplitude, which corresponds to this E naught here, the sine function, which is the oscillating function, which is what we want for strings that are oscillating back and forth, and for electromagnetic waves that are oscillating back and forth. This first term inside here is 2 pi times f, which is the frequency, multiplied by t, just like we have above. And our second term over here, second term, 2 pi over lambda, where lambda is the wavelength. You might remember that being called L when we're studying standing waves on a string. When it comes to electromagnetic waves, we use lambda to describe the wavelength, but it's essentially the same thing. Now, by comparing these values, we can go ahead and look for the frequencies, the first thing we want to know here. So this frequency, f, 2 pi f, is equal to 1.5 times 10 to the 10 seconds to the minus 1. So just looking at those first terms in each of the equations, they're going to be equal to each other. You'll also see that we are keeping our units of s to the minus 1. That's oscillations per second. If we just divide by 2 pi on sides now, let me go ahead and write that out, and divide both sides of this equation by 2 pi. Then we see that the frequency is equal to about 2.4 times 10 to the 9th. That's seconds to the minus 1, also known as hertz. Might have heard that as a unit for frequency. And that's the first part of this problem. Now, if we want to take a look at the second part of the problem, what we want to do is find the distance between nodes. So let's take a look over here at a wave. So we have some kind of wave like this. The nodes are these points. Basically, the points, if this was a vibrating string oscillating back and forth, those are the points where it's not actually moving up and down. It's stuck at those points. We call those the nodes. And this distance between nodes is actually equal to 1/2 the wavelength. So an entire wave goes up, down, and back up. And so this entire wavelength cut in half is where each of those nodes lie. So to figure out this second part of the problem, what we need to do is solve for lambda, the wavelength. Going back to our equation over here, we have 2 pi over lambda is equal to 5.0 times 10 meters to the minus 1. Again, meters to the minus 1, that's because meters is on the bottom of our units. That's like 1 over meters, which is because lambda here is in the denominator. But first thing that I want to do is move lambda out of the denominator. So I'm going to multiply by lambda on both sides of that equation. This becomes 2 pi equals 5.0 times 10 lambda. And now, in order to isolate that wavelength lambda, I'm going to divide by this value here on both sides of the equation. And what we'll get is that, I'll bring it up over here. What we'll get is that lambda is equal to about 1.25 times 10 to the minus 1 meters. Now that's lambda. That's this entire wavelength from here to here. But like we said earlier, the nodes are breaking that wavelength up in half. So all we need to do to find the distance between nodes, call that distance between nodes, is to just take lambda 1.25 times 10 to the minus 1 meters and divide it by 2. Just cut it right in half. And what we get is about 6.28 times 10 to the minus 2 meters. That's how far apart those nodes are in this electromagnetic wave.